Before we begin, let's look at examples of some common chemical reactions, like the burning of coal. When coal is burned, the chemical energy stored in the molecules is released as heat or thermal energy. Another example is that of burning of fuel in a car engine. When the fuel burns in an engine, it converts the chemical energy to mechanical energy, propelling the car to move along the road. In both the examples, chemical energy, that is the energy stored in the bonds of atoms and molecules, is converted to other forms of energy. Thus, various forms of energy are interrelated, and under certain conditions, these may be transformed from one form to another. The branch of science that deals with the study of different forms of energy and the quantitative relationship between them is known as thermodynamics. The term thermodynamics is derived from the Greek word thermos, meaning heat, and dynamics, meaning flow. It was coined by James Joule in the early 19th century. Thermodynamics deals with the energy changes within a system. A system in thermodynamics refers to that part of the universe in which observations are made. For example, the tea in the teapot is a system. The part of the universe that is not a part of the system but can interact with the system is called a surrounding. In this case, the room in which the teapot is kept is the surrounding. Systems and surroundings together constitute the universe. The part that separates a system from its surrounding is known as boundary. In this case, the wall of the teapot is the boundary. Note that a boundary can be real or imaginary, and it controls the flow of energy and matter into the system or out of the system. In thermodynamics, based on the movements of matter and energy between a system and its surroundings, systems can be classified into three types. These are open system, closed system, and isolated system. Let's look at each system. A system is said to be open if it can exchange both energy and matter with its surroundings. For example, tea becomes cold when left open for some time in a container as a result of exchange of energy with the surroundings. At the same time, some amount of tea escapes from the cup as vapor. This is because of exchange of matter with the surroundings. Hence, this is an example of an open thermodynamic system. A system which permits the exchange of energy but not the exchange of matter across the boundary with its surroundings is called a closed system. For example, if tea is kept in a closed steel teapot, it takes some time to cool down. This indicates that energy is exchanged with the surroundings. However, as vapor cannot escape from the container, no exchange of matter is possible. Hence, this stands as an example for a closed thermodynamic system. A system that can exchange neither energy nor matter with its surroundings is called an isolated system. For example, the tea kept in a thermos flask remains hot and the vapor also doesn't escape out. This is because neither matter nor energy can be exchanged with the surroundings. Hence, this is an example of an isolated thermodynamic system. You have learned that a system is a part of the universe in which observations are made. In order to make these observations, it is important that we know the state of the system. By state of a system, we mean the condition of the system in terms of measurable, macroscopic properties such as temperature T, pressure P, and volume V, to name a few. The first state of the system, that is, the state before the change, is called the initial state, and the last state, that is the state after the change, is called the final state. As a change in the magnitude of these properties changes the state of a system, these properties are called state variables or state functions. In other words, properties whose values depend only upon the initial and final states of the system and are independent of the manner in which the change is brought about are called state functions. Macroscopic properties, on which the state of a system depends, are further divided into extensive properties and intensive properties. Extensive properties are properties that depend upon the quantity of the matter contained in a system. Examples of extensive properties are mass, volume, and heat capacity. For example, 200 milliliters of water takes up more volume than 100 milliliters of water. Intensive properties are properties that are independent of the amount of the substance present in the system. Some examples of intensive properties are temperature, pressure, freezing point, and boiling point. For example, boiling point is an intensive property because whatever be the quantity of water, it always boils at 100 degrees Celsius. When the state of a system changes, it implies that some thermodynamic process has occurred on the system, and energy has been either added to it or removed from it. The energy stored within a substance or a system is known as the internal energy of the system. In other words, internal energy is the sum of all the possible kinds of energy of a system. Internal energy is represented by capital U. The absolute value of internal energy cannot be found. However, change in it, represented by delta U, can be found. Internal energy U changes when work is done on or by the system. Heat passes into or out of the system. Matter enters or leaves the system. Let us discuss the change in internal energy brought out by work done on the system. Let us take a certain amount of water in a thermos flask or an insulated vessel that does not allow heat exchange with the surroundings. Such a system is called an adiabatic. The state of such a system changes without an exchange of heat, and thus the process is called an adiabatic process. In other words, delta Q is equal to 0. We can bring a change in internal energy in a system by two ways. In the first method, internal energy can be increased by doing some mechanical work. For example, by churning the water. Let UA be the initial internal energy of the system at temperature TA. After churning, internal energy changes to UB as temperature increases to TB. Thus, the change in internal energy is given by delta U is equal to UB minus UA. In the second method, internal energy can be increased by the same amount by doing electrical work. In this, an immersion rod is kept in water and the temperature before and after is measured. We find the change in temperature as Tb minus Ta. Hence, the change in internal energy, delta U, equal to Ub minus Ua. Thus, internal energy changes to the same extent either by doing mechanical work or electrical work, which indicates that it is independent of the manner in which the change is brought about. Therefore, internal energy is a state function. If work is done on the system, then U increases and W is considered as positive. On the other hand, if work is done by the system, then U decreases and W is considered as negative. A change in internal energy can also be brought out by the transfer of heat. Heat transfer takes place from the system to the surroundings, or vice versa. The exchange of energy due to temperature difference is called heat Q. Therefore, delta U is equal to Q. Q is positive if heat transfers from the surroundings to the system, and negative if heat transfers from the system to the surroundings. If heat transfers from the surroundings to the system, then internal energy increases, and hence Q is considered as positive. On the other hand, if heat transfer takes from the system to the surroundings, then internal energy decreases. That is, Q is negative. When a change in the state of a system occurs, energy is transferred either to or from the surroundings. This energy may be transferred as heat or mechanical work. In thermodynamics, the only type of work generally considered is the work done in expansion or compression of a gas. This is known as pressure volume work or PV work. Let us understand this better with an example. Consider a cylinder filled with 1 mole of an ideal gas and fitted with a frictionless piston. Let's say the area of the cross-section of the cylinder is A square centimeter. The pressure of the gas inside the cylinder is P, and the volume of the gas inside the cylinder is VI. Here, VI stands for the initial volume of the gas. Now, let's apply external pressure PEX on the piston. If the external pressure PEX is greater than the internal pressure P, then the piston moves inwards until the pressure P inside the cylinder becomes equal to the external pressure PEX. Let this change be achieved in a single step. At this stage, the final volume of the system is represented by Vf, and the distance that the piston is moved is represented by L. Thus, the change in the volume, that is, final volume Vf minus initial volume Vi, is distance L multiplied by area A. We know that pressure equals force divided by area. Hence, the applied force F on the piston equals pressure multiplied by area. That is, the applied force F equals external pressure PEX multiplied by the area of cross-section A. If W is the work done on the system by the movement of the piston, Then, work equals force multiplied by distance. But force equals external pressure. That is, PEX multiplied by area of cross-section A. Substituting the value of force in the equation for work, we get work is equal to external pressure PEX multiplied by area A multiplied by distance L. But distance L multiplied by area A gives change in volume delta V. On substituting, we get work equals external pressure PEX multiplied by minus change in volume delta V. That is, work is equal to minus external pressure PEX multiplied by final volume VF minus initial volume VI. The negative sign is added in the expression to obtain the conventional sign for W. According to the latest SI conventions, W is taken as positive if work is done on the system, that is, the work of compression. And W is taken as negative if the work is done by the system, that is, the work of expansion. Therefore, the general expression for work done is written as W equals minus external pressure PEX multiplied by change in volume delta V, which is equal to minus external pressure PEX multiplied by final volume VF minus initial volume VI. The expression of work applies for both expansion and compression of a gas. If the gas expands, VF will be greater than VI. Then, we can say that work is done by the system. Hence, the value of work done will be negative. Similarly, if the gas compresses, VF will be lesser than VI. On substituting the values of volume in the equation of work, we get a negative volume. When this negative value is multiplied with the negative external pressure, the resultant work is positive. Then we can say that work is done on the system. If the pressure is not constant and changes in finite numbers of steps for every stage of compression, then the work done is calculated as W equals minus the summation of pressure multiplied by change in volume. When these values are plotted on a graph, the work done on the gas is visible in the shaded area. However, if the pressure is not constant and varies such that it is always infinitesimally greater than the pressure of the gas at each stage of compression, the volume decreases by an infinitesimal amount dV. Then, work is equal to minus F integral of external pressure PEX multiplied by infinitesimal change in volume dV. If gas expands, then the external pressure is always less than the pressure of the system. Thus, PEX at each stage is equal to the difference between the internal pressure P and infinitesimal change in pressure of the system dP. If gas is compressed, then the external pressure is always greater than the pressure of the system. Thus, the PEX at each stage is equal to the sum of the internal pressure P and infinitesimal change in pressure dP. Therefore, external pressure applied on a system is expressed as external pressure equals internal pressure plus or minus infinitesimal change in the pressure of the system. This is known as reversible process. Thus, a reversible process is one that takes place infinitesimally slowly and the direction of which at any point can be reversed by an infinitesimal change in the state of the system. In a reversible process, the system is in equilibrium in the initial, final, and all intermediate stages. To understand this, let's assume that there is a cylinder with a frictionless piston. Now, let's place few grains of sand above the piston and allow the gas to compress by adding 1 grain of sand at a time. Here, the process is so slow that it can be easily reversed by removing 1 grain of sand at any time. This is known as reversible process. Processes which are not reversible are known as irreversible processes. Under reversible conditions, the relationship between work and internal pressure is written as reversible work equals minus integral of external pressure PEX with respect to infinitesimal change in volume dV. We know that external pressure PEX equals internal pressure P in plus or minus infinitesimal change in pressure of the system dP. Thus, on substituting the values, we get the equation reversible work equals minus integral of internal pressure P in plus or minus infinitesimal change in pressure of the system dP multiplied by infinitesimal change in volume dV. As change in the pressure and volume are infinitesimally small, their product is still smaller. Therefore, the product of infinitesimal change in pressure dP and infinitesimal change in volume dV can be neglected. Hence, the final equation is reversible work equals negative integral of P in multiplied by infinitesimal change in volume dV. Now, if we represent pressure of the gas P in terms of the ideal gas equation, then we get PV equals nRT or P equals nRT divided by V. On substituting the value of P at constant temperature in the reversible work equation, we get reversible work equals minus integral of nRT multiplied by infinitesimal change in volume dV by V. Integrating and applying limits as Vi for initial volume and Vf for final volume, we get reversible work W rev is equal to minus nRT ln final volume Vf divided by initial volume Vi. On converting natural logarithm to base 10, we get reversible work W rev equals minus 2.303 nRT log Vf by Vi. If the gas expands in vacuum, external pressure PEX being 0 in the expression W is equal to minus PEX multiplied by delta V, W becomes 0. This is known as free expansion. No work is done during the free expansion of an ideal gas, whether the process is reversible or irreversible. We know that according to the first law of thermodynamics, the change in internal energy is represented as delta U equals Q plus W. On substituting the value of W in the above equation, we get delta U equals Q plus minus PEX multiplied by delta V. If the process is carried out at constant volume, delta V is 0. Therefore, work done is also 0. Hence, at constant volume, delta U equals QV, where QV is heat supplied at constant volume. We have learned that if a process is carried out at constant volume, then the heat content is the same as the internal energy as no work is done. But most of the chemical reactions are carried out at constant pressure and not at constant volume. When a reaction is performed under constant pressure, then it may involve change in the volume. The energy change occurred during such reactions may not only involve change in internal energy but also do some work. To understand this, assume a chemical reaction occurring at a constant pressure. Let us assume that the reaction is exothermic and also involves gaseous substances. When the reaction proceeds at constant pressure, two possibilities arise. One possibility is that if the reaction is carried out with increase in volume, then the system has to expand against atmospheric pressure and energy is required to perform this act. As some of the energy has to be utilized for this purpose, the heat evolved in this case would be a little less than the heat evolved at constant volume conditions. The other possibility is that if the reaction is carried out with decrease in volume at constant pressure, then the work is done on the system and heat evolved would be greater than the heat evolved at constant volume. Thus, it can be concluded that heat changes occurring at constant pressure and temperature are not only due to change in internal energy but also due to expansion or contraction against the atmospheric pressure. Hence, the scientists felt the need to study the heat changes at constant pressure and temperature. In order to study the heat changes in a chemical reaction at constant temperature and constant pressure, a new thermodynamic function called enthalpy was introduced. The total heat content of a system at constant pressure is equal to the sum of the internal energy and PV. This is called the enthalpy of a system, which is represented by H. Note that enthalpy is also called as heat content. Enthalpy, which depends on the three state functions, internal energy, pressure, and volume, is also a state function. Every substance has a definite value of enthalpy. Like internal energy, enthalpy of a substance cannot be measured. However, it is possible to measure the change in enthalpy. The change in enthalpy is equal to the difference between enthalpy of products and enthalpy of reactants. The change in enthalpy may be expressed as delta H is equal to enthalpy of products, HP, minus enthalpy of reactants, HR. The significance of delta H also follows from the first law of thermodynamics, as delta U is equal to QP minus P delta V. Here, QP represents the heat absorbed by the system and minus P delta V represents the work done by the system. Let U1, U2, V1 and V2 represent the initial and final internal energies and volumes respectively. The above equation can be written as U2 minus U1 equal to QP minus P into V2 minus V1. On rearranging this, we get QP equal to U2 plus PV2 minus U1 plus PV1. But we've already learned that U plus PV equal to enthalpy H. Hence, the equation can be written as QP equal to H2 minus H1 is equal to delta H. Therefore, delta H is equal to QP. For finite changes at constant pressure, we can write the equation as delta H is equal to delta U plus delta PV. Since P is constant, we can write as delta H is equal to delta U plus P delta V. Remember that delta H is equal to QP, the heat absorbed by the system at constant pressure. Delta H is negative for exothermic reactions and positive for endothermic reactions. Let's now look at the relation between delta H and delta U. When we deal with solids and liquids, the difference between the change in internal energy, delta U, and enthalpy, delta H, is not significant. This is because solids and liquids do not show significant change in the volume when heated. Thus, if change in volume, delta V, is insignificant, it implies that change in enthalpy, delta H, equals change in internal energy, delta U. The difference between the change in internal energy and enthalpy becomes significant when gases are involved in the reaction. Let's consider a chemical reaction occurring at constant temperature, T, and constant pressure, P. Now, let's say that the volume of the reactants is VA and the number of moles in the reactants is Na. Similarly, the volume of the products is VB and the number of moles in the product is NB. We know that according to the ideal gas equation, PV equals nRT. Thus, for the reactants, PVA equals NART, and for the products, PVB equals NBRT. Thus, PVB minus PVA equals NBRT minus NART, or PVB minus VA is equal to NBRT minus NART, or PVB minus VA equal to NB minus NART. That is, pressure P multiplied by change in volume, delta V equals change in number of moles of gas, delta N GRT. Note that delta N is the number of moles of gaseous products minus number of moles of gaseous reactants. We learned that change in enthalpy delta H equals change in internal energy delta U plus product of pressure P and change in volume delta V. On substituting the values, we get change in enthalpy delta H equals change in internal energy delta U plus change in number of moles of gas delta N GRT. This relation helps us in calculating the change in enthalpy from change in internal energy and vice versa. Now let's learn about heat capacity. The capacity to absorb heat energy and store it is known as the heat capacity of a system. The heat absorbed by the system appears as rise in temperature. The increase in temperature is proportional to the heat transferred, which can be written as Q equals coefficient multiplied by change in temperature delta T. Note that the value of the coefficient depends on the size, composition, and nature of the system. The equation can also be written as Q equals C multiplied by delta T, where C is called the heat capacity of the system. If Q calories is the heat absorbed by the system and the temperature rises from T1 to T2, the heat capacity C is given by the expression C equal to Q by T2 minus T1. Thus, heat capacity is defined as the amount of heat required to raise the temperature of the system by 1 degree at a specified temperature. The specific heat capacity is the quantity of heat required to raise the temperature of unit of mass of a substance by 1 degree Celsius or by 1 Kelvin. Thus, the expression for Q in terms of specific heat capacity becomes Q equals specific heat capacity C multiplied by the mass m multiplied by change in temperature delta T. The molar heat capacity of a substance is defined as the quantity of heat needed to raise the temperature of 1 mole of substance through 1 degree Celsius or 1 Kelvin. The SI unit of molar heat capacity is Joule per degree Kelvin per mole. The molar heat capacity Cm equals heat capacity C divided by N, where N is the amount of the substance. Heat is not a state function, neither is heat capacity. Hence, it is necessary to specify the process by which the temperature is raised by 1 degree. The two important types of molar capacities are molar heat capacity at constant volume and molar heat capacity at constant pressure. Let us see the relation between molar heat capacity at constant volume, which is denoted by Cv, and molar heat capacity at constant pressure, which is denoted by Cp. We learned that the equation for heat, Q, is the product of heat capacity and change in temperature, delta T. Therefore, at constant volume, heat, Qv, equals product of heat capacity at constant volume, Cv, and change in temperature, delta T. But the heat absorbed at constant volume is equal to change in internal energy. Thus, Cv into delta T can be written as equal to delta U. Similarly, at constant pressure, heat, Qp, equals product of heat capacity at constant pressure, Cp, and change in temperature delta T. We have seen that at constant pressure the heat absorbed by the system is equal to the change in enthalpy. Hence, Cp into delta T can be written as equal to delta H. The difference between Cp and Cv for 1 mole of an ideal gas can be derived as follows. The change in enthalpy for 1 mole of an ideal gas can be written as delta H equals delta U plus delta PV. For 1 mole of an ideal gas, PV is equal to RT. Hence, the equation can be written as delta H equals delta U plus delta RT. As R is constant, the equation can also be written as delta H equal to delta U plus R delta T. On substituting the values of delta H and delta U in the equation, we get Cp multiplied by delta T equals Cv multiplied by delta T plus R delta T. Since delta T is equal to 1, we can write the equation as Cp equal to Cv plus R, or Cp minus Cv is equal to R. Calorimetry is an experimental technique that involves the measurement of heat changes associated with physical or chemical processes. In laboratory, such changes are measured in a calorimeter. These measurements are generally carried out under two conditions: at constant volume, QV, and at constant pressure, QP. The experimental technique of calorimetry actually involves two steps. First step is the determination of heat capacity of a calorimeter. The second step involves the determination of the change in temperature during the completion of the reaction, assuming that it is an insulated system and no heat is exchanged with the surroundings. Let us first discuss the measurement of heat change at constant volume, or the internal energy change, delta U. The reactions that can be most easily studied under constant volume conditions are the combustion reactions, and the apparatus used for this purpose is called the bomb calorimeter. It consists of a sealed constant volume steel container known as the bomb, in which the reaction takes place. The bomb can withstand high pressures. A known mass W grams of a combustible substance is placed in the bomb, and oxygen under high pressure is introduced into the bomb. The sealed bomb is then immersed in a known amount of water contained in an insulated container. As the container is insulated, there is no heat exchange with the surroundings, and the reaction process is adiabatic. This whole setup is called the bomb calorimeter. The sample is ignited electrically, and the heat produced by the combustion reaction is absorbed by the water surrounding the bomb. The increase in temperature of water, delta T, is noted, and the heat produced is calculated using the equation QV is equal to CV multiplied by delta T, where CV is the heat capacity of the calorimeter. The measure of a bomb calorimeter's heat absorbing property is called its heat capacity. Each bomb calorimeter differs from all others in its ability to absorb or release heat. The heat capacity of each bomb calorimeter is determined experimentally. Heat capacity of the calorimeter is determined separately by igniting a known amount of a substance, whose heat of combustion is already known, in the same calorimeter. And CV is equal to C multiplied by M, where C is the specific heat of water and is equal to 4.184 joules per Kelvin per gram, and M is the mass of water. Actually, heat capacity of the calorimeter or the system is the sum of heat capacity of the bath, that is, water, and the heat capacity of the bomb, that is, the metal. Water has high value of heat capacity as compared to the metal of the bomb. Thus, heat capacity of the metal is neglected, and the heat capacity of the calorimeter is taken as the heat capacity of only the bath. This QV expressed above is the heat evolved when combustion of W grams of the substance takes place. Since heat of combustion is defined as the combustion of 1 mole of a substance, therefore, the expression for molar heat of combustion becomes molar heat of combustion is equal to CV multiplied by delta T multiplied by M by W, where W is the mass of the substance taken and M is the molecular weight of that substance. As the above reaction is carried out in a closed vessel, therefore, heat evolved is the heat of combustion at constant volume and is a measure of internal energy change, delta U. Let us now measure the heat changes at constant pressure. To measure the heat changes at constant pressure, a device known as a coffee cup calorimeter is used. These calorimeters are open to the atmosphere, so these measure heat changes at constant pressure. This calorimeter is a foamed polystyrene cup partially filled with a known volume of water and fitted with a stirrer and a thermometer inserted through the lid of the cup. When a reaction occurs in the coffee cup calorimeter, the heat change is measured in terms of the change in the temperature of the system. Heat flow in the system is calculated by using the relation QP is equal to specific heat multiplied by M multiplied by delta T, where QP is the heat flow in the system, M is the mass of water in the coffee cup in grams, and delta T is the change in temperature. Specific heat of water is taken as 4.184 joules per Kelvin per gram. Therefore, the formula for calculating molar enthalpy delta H substance is delta H is equal to M multiplied by specific heat of water multiplied by delta T divided by N, where N is the number of moles of the reacting substance in the system. It is important to note that when heat is absorbed or evolved by the system at constant pressure, we are actually measuring changes in the enthalpy. Therefore, delta H is equal to QP. In an exothermic reaction, heat is evolved and the system loses heat to the surroundings. Therefore, QP as well as enthalpy change delta H is negative. Similarly, for an endothermic reaction, heat is absorbed by the system from the surroundings and therefore QP as well as the enthalpy change delta H will be positive. The enthalpy change that accompanies a reaction is called reaction enthalpy or enthalpy of reaction. The enthalpy change that accompanies a reaction is called reaction enthalpy or enthalpy of reaction. The enthalpy of a reaction is defined as the amount of heat evolved or absorbed in a chemical reaction when the number of moles of the reactants as expressed in the chemical equation have completely reacted. Enthalpy change of a reaction is denoted by delta RH. Enthalpy of a reaction is expressed as the summation of enthalpies of products minus the summation of enthalpies of reactants, where AI and BI are the stoichiometric coefficients of the products and reactants respectively in the balanced chemical equation. For example, the enthalpy changes for the reaction of 1 mole of methane with 2 moles of oxygen forming 1 mole of carbon dioxide and 2 moles of water may be represented as follows. The knowledge of reaction enthalpy helps us in maintaining the conditions required to carry out the industrial chemical reactions at constant temperature. It also helps in calculating the temperature dependence of equilibrium constant. The enthalpy of any reaction depends on the conditions under which it is carried out. Thus, it's difficult to compare the enthalpy reaction value for different reactions. To overcome this problem, the values of delta H for different reactions are expressed at their standard state conditions. The standard enthalpy of a reaction is the enthalpy change accompanying the reaction when all the reactants and products are taken in their standard states. A substance is said to be in a standard state when it is present in its most pure state under a pressure of 1 bar at a specified temperature. In other words, when the enthalpy of a reaction occurs at 1 bar pressure and specified temperature, it is called standard enthalpy. For example, the standard state of liquid ethanol is pure liquid ethanol at 298 Kelvin and 1 bar pressure, and the standard state of solid iron is pure iron at 500 Kelvin and 1 bar pressure. Let us now look at the enthalpy changes during phase transformations. We know that the intermolecular forces in the 3 states of matter are different. Therefore, the amount of energy required to convert matter from one state to another also differs. Standard enthalpy is represented as delta H naught, where the superscript naught indicates the standard state. The process by which matter is converted from one state into another is known as phase change or phase transition. The enthalpy or heat changes accompanying these phase changes are enthalpy of fusion, enthalpy of vaporization, and enthalpy of sublimation. Let's look at each type in detail. Standard enthalpy of fusion is the enthalpy change accompanying the melting of 1 mole of a solid substance in standard state into its liquid state. It is also called as molar enthalpy of fusion and is represented as delta fusion H naught. For example, the amount of heat required to melt 1 mole of ice at 273 Kelvin is 6 kilojoules. Thus, we can say that the molar enthalpy of fusion of ice is plus 6 kilojoules per mole. As the melting of a solid is an endothermic process, all enthalpies of fusion are positive. We know that freezing is the reverse of fusion. Thus, the enthalpy of freezing, also known as enthalpy of solidification, is the same as enthalpy of fusion, except that it has the opposite sign, that is, a negative sign. Now let's look at the enthalpy of vaporization. The amount of heat required to convert 1 mole of a liquid into its vapor state at constant temperature and under standard pressure is called its standard enthalpy of vaporization or molar enthalpy of vaporization. For example, the amount of heat required to convert 1 mole of water into vapor at temperature 373 Kelvin is 40.79 kilojoules. Thus, the molar enthalpy of vaporization of water is plus 40.7 kilojoules per mole. We know that condensation is the opposite of vaporization. Thus, the enthalpy of condensation has the same value as the enthalpy of vaporization, except that it has the opposite sign, that is, the negative sign. Now, let's look at the enthalpy of sublimation. Sublimation is a process in which a solid changes directly into vapor state without any intermediate liquid state. Enthalpy of sublimation is defined as the enthalpy change accompanying the conversion of 1 mole of a solid directly into vapor phase at constant temperature and under standard pressure. For example, the amount of heat required to sublime 1 mole of iodine is 62.4 kilojoules. Thus, we can say that the molar enthalpy of sublimation of iodine is plus 62.4 kilojoule per mole. The magnitude of the enthalpy change in phase transformations depends on the strength of the intermolecular interactions between the molecules in the substance undergoing phase change. For example, it requires about 40.79 kilojoules of energy to vaporize 1 mole of water, while it requires only 29 kilojoules of energy to vaporize 1 mole of acetone. This can be explained in accordance to the fact that the water molecules are held together in the liquid state through hydrogen bonding, while the acetone molecules are held together only through weaker dipole-dipole interactions. Thus, it requires less heat to vaporize 1 mole of acetone than 1 mole of water. The enthalpy change associated with the formation of 1 mole of a compound from its constituent elements, all substances being in their standard states, that is, at 298 Kelvin and 1 bar pressure, is called the standard molar enthalpy of formation. It is represented as delta FH naught. The subscript F indicates that 1 mole of compound has been formed in its standard state from its elements in their most stable states. For example, when carbon and oxygen in their elemental states react to form 1 mole of carbon dioxide, 393.5 kilojoules of heat is produced. Hence, we can say that the standard enthalpy formation of gaseous carbon dioxide is minus 393.5 kilojoules per mole. However, the reaction of formation of water from its elements does not represent the standard enthalpy of formation of water. This is because the heat, 571.6 kilojoules per mole, is evolved when 2 moles of water are formed from the elements at the standard state. This can be referred as enthalpy of reaction. The standard enthalpy of formation in this case would be minus 571.6 divided by 2. That is, minus 285.8 kilojoules per mole. By convention, the standard enthalpy of formation of all elements is assumed to be 0. We can calculate the heat of reaction under standard conditions from the values of standard heat of formation of various reactants and products. The standard enthalpy of reaction can be calculated as the sum of standard enthalpies of formation of products minus the sum of standard enthalpies of formation of reactants. Let's see how we can apply this formula. Let's say that we have to determine the amount of heat required to decompose calcium carbonate to lime and carbon dioxide, given that all the substances are in their standard state. We can use the formula of standard enthalpy of reaction to determine the enthalpy change of the reaction. Thus, we get enthalpy of reaction equals enthalpy of formation of products, that is, lime and carbon dioxide, minus enthalpy of formation of the reactant, that is calcium carbonate. On substituting the values of standard molar enthalpy of formation of the reactants and products from the table of standard molar enthalpy of formation of substances, we get the amount of heat as plus 178.3 kilojoules per mole. Thus, the plus value of the standard enthalpy of reaction indicates that the decomposition of calcium carbonate is an endothermic reaction. Note that the stoichiometric coefficients for all the compounds in the given equation are 1. Now, let us look into the thermochemical equations. Hess's law states that if a chemical change can be made to take place in 2 or more different ways, whether in one step or more than one step, the amount of total heat change is the same no matter by which method the change is brought about. For example, the enthalpy of an overall reaction A gives rise to B along one route is delta RH. Now, if the same reaction occurs through another route, delta RH1, delta RH2, delta RH3, then we can say that delta RH equals the sum of delta RH1, delta RH2 and delta RH3. Let's understand this through a chemical reaction. When sulfur in its elemental state burns to form sulfur trioxide in one step, the heat evolved during the chemical equation is minus 395.4 kilojoules per mole. Now, let's break down the reaction into two steps. In the first step, sulfur reacts with oxygen to form sulfur dioxide. The heat evolved during the chemical equation is minus 297.5 kilojoules per mole. In the second step, sulfur dioxide reacts with oxygen to form sulfur trioxide. The heat evolved during the chemical equation is minus 97.9 kilojoules per mole. If we add the heat evolved from both steps, we get minus 395.4 kilojoules per mole. Note that the amount of heat evolved through the two steps is the same as the amount of heat evolved in one step, thus proving Hess's law. Combustion is a process of burning a chemical compound at high temperatures in presence of excess of oxygen or air. Combustion reactions are exothermic reactions. The energy released during these reactions is used to drive automobiles, ships, airplanes and trains, to operate industrial processes, rocketry, and for numerous other purposes. The energy change accompanying the process of combustion is called the enthalpy of combustion. It is defined as the amount of heat energy evolved when 1 mole of substance is completely burnt or oxidized in excess of air or oxygen, and is represented as delta CH. For example, when 1 mole of carbon is completely burnt, it releases 393.5 kilojoules of heat. The negative sign of enthalpy change indicates the exothermic nature of the reaction. The enthalpy of combustion is considered only if the substance oxidizes completely. For example, if carbon is oxidized to form carbon monoxide, then the heat of the reaction is minus 110.5 kilojoules per mole. Since carbon does not oxidize completely, the heat evolved during the reaction is not considered as the enthalpy of combustion. Standard enthalpy of combustion is defined as the enthalpy change per mole of a substance when it undergoes combustion, with all the reactants and products being in their standard states at the specified temperature. It is represented by delta CH0. Combustion reactions release large amounts of energy. For example, 1 mole of butane on complete combustion produces minus 2658 kilojoules per mole of energy. The energy released by the combustion of food or fuel is usually compared in terms of their combustion energy per gram, which is known as calorific value. Calorific value of food or fuel is defined as the amount of heat released by the complete combustion of 1 gram of fuel or food. Calorific value is usually expressed in kilojoules per gram or kilocalorie per gram. When 1 mole of glucose burns, it releases 2820 kilojoules of heat. Hence, the calorific value of glucose is 2820 divided by 180, which is equal to 15.67 kilojoules per gram. Now let's look at enthalpy of atomization. When 1 mole of a given substance dissociates into gaseous atoms, the enthalpy change accompanying the process is called the standard enthalpy of atomization. It is represented by delta AH0. Let's consider the atomization of dihydrogen into hydrogen atoms. In this reaction, hydrogen atoms are formed by breaking of HH bonds in dihydrogen. The conversion of 1 mole of hydrogen molecules into hydrogen atoms requires 435.5 kilojoules per mole of energy. Therefore, the enthalpy of atomization of dihydrogen is 435.5 kilojoules per mole. Now let's look at bond enthalpy. We know that chemical reactions involve the breaking and making of bonds. The breaking of bonds requires energy, while the making of bonds involves the release of energy. The enthalpy changes associated with chemical bonds are expressed in terms of bond dissociation enthalpy and mean bond enthalpy. Let us try to understand these terms with reference to diatomic and polyatomic molecules. In case of diatomic molecules, bond dissociation enthalpy is the change in enthalpy when 1 mole of covalent bonds of a gaseous covalent compound is broken to form products in the gas phase. For example, a 435.5 kilojoule per mole of energy is required to dissociate 1 mole of hydrogen gas into hydrogen atoms. Hence, the bond dissociation enthalpy of hydrogen is 435.5 kilojoules per mole. Note that this is the same as the enthalpy of atomization of hydrogen gas. For all diatomic molecules, bond dissociation enthalpy is the same as atomization enthalpy. In case of polyatomic molecules, bond dissociation enthalpy is different for different bonds within the same molecule. For example, the enthalpy of atomization of methane is 1665 kilojoules per mole. Although the 4 CH bonds are identical in terms of bond length and energy, the energy required to break individual CH bonds in each successive step is not the same. The energies required to break these bonds are successively plus 427, plus 439, plus 452, and plus 347 kilojoules per mole, respectively. The total energy required is plus 1665 kilojoules per mole. Hence, in such cases, we use the term mean bond enthalpy instead of bond dissociation enthalpy. Thus, mean CH bond enthalpy in methane is 416 kilojoules per mole. Bond enthalpies can be calculated using Hess's law. The knowledge of bond enthalpies helps us in predicting the enthalpy of a reaction in gas phase. The standard enthalpy of a reaction, delta RH0, is equal to sigma bond enthalpies of reactants minus sigma bond enthalpies of products. It is important to remember that this relationship is approximate and valid only when all the reactants and products in the reaction are in gaseous state. We have learned that if a process is carried out at constant volume, then the heat content is the same as the internal energy as no work is done. But most of the chemical reactions are carried out at constant pressure and not at constant volume. When a reaction is performed under constant pressure, then it may involve change in the volume. The energy change occurred during such reactions may not only involve change in internal energy but also do some work. To understand this, assume a chemical reaction occurring at a constant pressure. Let us assume that the reaction is exothermic and also involves gaseous substances. When the reaction proceeds at constant pressure, two possibilities arise. One possibility is that if the reaction is carried out with increase in volume, then the system has to expand against atmospheric pressure and energy is required to perform this act. As some of the energy has to be utilized for this purpose, the heat evolved in this case would be a little less than the heat evolved at constant volume conditions. The other possibility is that if the reaction is carried out with decrease in volume at constant pressure, then the work is done on the system and heat evolved would be greater than the heat evolved at constant volume. Thus, it can be concluded that heat changes occurring at constant pressure and temperature are not only due to change in internal energy but also due to expansion or contraction against the atmospheric pressure. Hence, the scientists felt the need to study the heat changes at constant pressure and temperature. In order to study the heat changes in a chemical reaction at constant temperature and constant pressure, a new thermodynamic function called enthalpy was introduced. The total heat content of a system at constant pressure is equal to the sum of the internal energy and PV. This is called the enthalpy of a system, which is represented by H. Note that enthalpy is also called as heat content. Enthalpy, which depends on the three state functions, internal energy, pressure, and volume, is also a state function. Every substance has a definite value of enthalpy. Like internal energy, enthalpy of a substance cannot be measured. However, it is possible to measure the change in enthalpy. The change in enthalpy is equal to the difference between enthalpy of products and enthalpy of reactants. The change in enthalpy may be expressed as delta H is equal to enthalpy of products, HP, minus enthalpy of reactants, HR. The significance of delta H also follows from the first law of thermodynamics, as delta U is equal to QP minus P delta V. Here, QP represents the heat absorbed by the system and minus P delta V represents the work done by the system. Let U1, U2, V1 and V2 represent the initial and final internal energies and volumes respectively. The above equation can be written as U2 minus U1 equal to QP minus P into V2 minus V1. On rearranging this, we get QP equal to U2 plus PV2 minus U1 plus PV1. But we've already learned that U plus PV equal to enthalpy H. Hence, the equation can be written as QP equal to H2 minus H1 is equal to delta H. Therefore, delta H is equal to QP. For finite changes at constant pressure, we can write the equation as delta H is equal to delta U plus delta PV. Since P is constant, we can write as delta H is equal to delta U plus P delta V. Remember that delta H is equal to QP, the heat absorbed by the system at constant pressure. Delta H is negative for exothermic reactions and positive for endothermic reactions. Let's now look at the relation between delta H and delta U. When we deal with solids and liquids, the difference between the change in internal energy, delta U, and enthalpy, delta H, is not significant. This is because solids and liquids do not show significant change in the volume when heated. Thus, if change in volume, delta V, is insignificant, it implies that change in enthalpy, delta H, equals change in internal energy, delta U. The difference between the change in internal energy and enthalpy becomes significant when gases are involved in the reaction. Let's consider a chemical reaction occurring at constant temperature, T, and constant pressure, P. Now, let's say that the volume of the reactants is VA and the number of moles in the reactants is NA. Similarly, the volume of the products is VB and the number of moles in the product is NB. We know that according to the ideal gas equation, PV equals nRT. Thus, for the reactants, PVA equals NART, and for the products, PVB equals NBRT. Thus, PVB minus PVA equals NBRT minus NART, or PVB minus VA is equal to NBRT minus NART, or PVB minus VA equal to NB minus NART. That is, pressure P multiplied by change in volume, delta V equals change in number of moles of gas, delta NGRT. Note that delta N is the number of moles of gaseous products minus number of moles of gaseous reactants. We learned that change in enthalpy delta H equals change in internal energy delta U plus product of pressure P and change in volume delta V. On substituting the values, we get change in enthalpy delta H equals change in internal energy delta U plus change in number of moles of gas delta NGRT. This relation helps us in calculating the change in enthalpy from change in internal energy and vice versa. Now let's learn about heat capacity. The capacity to absorb heat energy and store it is known as the heat capacity of a system. The heat absorbed by the system appears as rise in temperature. The increase in temperature is proportional to the heat transferred, which can be written as Q equals coefficient multiplied by change in temperature delta T. Note that the value of the coefficient depends on the size, composition, and nature of the system. The equation can also be written as Q equals C multiplied by delta T, where C is called the heat capacity of the system. If Q calories is the heat absorbed by the system and the temperature rises from T1 to T2, the heat capacity C is given by the expression C equal to Q by T2 minus T1. Thus, heat capacity is defined as the amount of heat required to raise the temperature of the system by 1 degree at a specified temperature. The specific heat capacity is the quantity of heat required to raise the temperature of unit of mass of a substance by 1 degree Celsius or by 1 Kelvin. Thus, the expression for Q in terms of specific heat capacity becomes Q equals specific heat capacity C multiplied by the mass m multiplied by change in temperature delta T. The molar heat capacity of a substance is defined as the quantity of heat needed to raise the temperature of 1 mole of substance through 1 degree Celsius or 1 Kelvin. The SI unit of molar heat capacity is Joule per degree Kelvin per mole. The molar heat capacity Cm equals heat capacity C divided by N, where N is the amount of the substance. Heat is not a state function, neither is heat capacity. Hence, it is necessary to specify the process by which the temperature is raised by 1 degree. The two important types of molar capacities are molar heat capacity at constant volume and molar heat capacity at constant pressure. Let us see the relation between molar heat capacity at constant volume, which is denoted by Cv, and molar heat capacity at constant pressure, which is denoted by Cp. We learnt that the equation for heat Q is the product of heat capacity and change in temperature delta T. Therefore, at constant volume, heat Qv equals product of heat capacity at constant volume Cv and change in temperature delta T. But the heat absorbed at constant volume is equal to change in internal energy. Thus, Cv into delta T can be written as equal to delta U. Similarly, at constant pressure, heat Qp equals product of heat capacity at constant pressure Cp and change in temperature delta T. We have seen that at constant pressure the heat absorbed by the system is equal to the change in enthalpy. Hence, Cp into delta T can be written as equal to delta H. The difference between Cp and Cv for 1 mole of an ideal gas can be derived as follows. The change in enthalpy for 1 mole of an ideal gas can be written as delta H equals delta U plus delta Pv. For 1 mole of an ideal gas, Pv is equal to RT. Hence, the equation can be written as delta H equals delta U plus delta RT. As R is constant, the equation can also be written as delta H equal to delta U plus R delta T. On substituting the values of delta H and delta U in the equation, we get Cp multiplied by delta T equals Cv multiplied by delta T plus R delta T. Since delta T is equal to 1, we can write the equation as Cp equal to Cv plus R, or Cp minus Cv is equal to R. Before we begin, let's look at this cold pack. Instant cold packs are often used by athletes for treating bumps and bruises. We know that a cold pack is not pre-cooled. Then, how does it become cold without being refrigerated? A cold pack contains 2 pouches, one filled with water and the other filled with a chemical substance. When the pack is squeezed, the pouches break and the chemical substance dissolves in water. The chemical reaction in the pouch absorbs heat energy from the surrounding. The temperature of the surrounding decreases, causing the pouch to become cold. The amount of heat energy released or absorbed when 1 mole of a substance dissolves in a specified amount of solvent is known as enthalpy of solution. For example, the ions of an ionic compound AB are held together by electrostatic forces of attraction. When it is dissolved in a solvent, its ions leave their ordered positions on the crystal lattice. Certain amount of energy is required for conversion of an ionic compound to its ions. This energy is known as lattice enthalpy and is denoted by delta lattice H0. Slowly these ions start moving freely in the solution and start interacting with the solvent particles. When water is used as a solvent, the dissolving process is called as hydration. If any other solvent is used, then the process is known as solvation of ions. Energy change occurs in dissolving of AB ions in the solvent is known as enthalpy of hydration of ions and is represented as delta hydration H0. As dissolution proceeds, the ions leave their lattice site and get mixed with the solvent. This total energy change of the solution is known as enthalpy of solution and is represented by delta solution H0. Thus, we can conclude that the enthalpy of solution of ionic compound AB is the sum of change in lattice enthalpy and enthalpy of hydration of ions. Let's look at the terms hydration enthalpy and lattice enthalpy. Enthalpy of hydration, delta hydration H0 of an ion is the amount of energy released when a mole of the ion dissolves in a large amount of water, forming an infinite dilute solution in the process. Lattice enthalpy, delta lattice H0 of an ionic compound is the enthalpy change which occurs when 1 mole of an ionic compound dissociates into its ions in gaseous state. The lattice enthalpy of a compound depends on the size of its ions and the charge on them. A decrease in the size of an ion increases the lattice enthalpy. That is, the enthalpy becomes negative and the reaction becomes exothermic. This happens because small ions tend to be closer to each other and have a shorter distance of separation, which results in a larger attraction force between the ions. Thus, lattice energy increases, that is, it becomes more negative. Alternatively, an increase in charge also increases the lattice enthalpy. That is, it becomes more negative. This is because the attraction forces between ions increases as the charge increases. It is not possible to determine lattice enthalpy through an experiment. But the same can be calculated by constructing an enthalpy diagram known as Born-Haber cycle. Let's look at an example. We know that the enthalpy change involved in the formation of a compound is called the enthalpy of formation. In this example, the enthalpy formation of sodium chloride from sodium in solid state and chlorine in gaseous state is minus 411 kilojoules per mole. Now, let's illustrate the different steps involved in the formation of sodium chloride. First, solid sodium changes to gaseous sodium atoms. The enthalpy change involved in this step is known as enthalpy of sublimation, and its value is plus 108.4 kilojoules per mole. In the next step, gaseous sodium atoms are ionized to form sodium +1 ions. The enthalpy change involved in this step is called ionization enthalpy, and its value is +496 kilojoules per mole. Similarly, the dissociation of chlorine takes place, and the enthalpy of dissociation is +121 kilojoules per mole. This is followed by chlorine atoms changing into chloride ions. Chlorine gains an electron, and the electron gain enthalpy is -348.6 kilojoules per mole. Finally, the gaseous ions combine to form solid sodium chloride. The enthalpy change involved at this step is known as lattice enthalpy. Let's apply Hess' law to determine the lattice enthalpy released in this step. Hess' law states that the enthalpy of change in a particular reaction is the same whether the reaction takes place in one step or in number of steps. Thus, enthalpy of formation equals enthalpy of sublimation of sodium plus enthalpy of dissociation of chlorine plus enthalpy of ionization of sodium plus electron gain enthalpy of chlorine plus lattice enthalpy. On substituting the values of all the enthalpies, we get the value of lattice enthalpy as -788 kilojoules per mole. We know that the first law of thermodynamics states that energy can neither be created nor destroyed, although it may be converted from one form to another. We also know that the transfer of energy usually occurs due to heat, Q, or work, W. While the first law explains the relationship between the heat absorbed and work done, it does not explain the direction of heat flow. For example, if we keep a cup of hot tea in a room, the law does not indicate whether the heat will flow from the hot cup to the cold surrounding or vice versa. The law only tells us that if a heat transfer process has occurred, then heat energy gained by one substance would be equal to heat energy lost by the other substance. If we observe closely, we'll notice that there is a natural direction in which processes take place. For example, if we keep a cup of hot tea in a room, we observe that the heat is transferred from the cup to the room. Thus, after a while, the hot tea cools down. Keep a cup of tea, which is at room temperature. Will the heat from the surrounding heat the cup? No, that is not possible. Similarly, water flows naturally from higher level to lower level, while we have to use a motor to transfer water from lower level to higher level. But why do these processes occur in a particular direction? The first law of thermodynamics does not answer this question, because it does not consider the feasibility or spontaneity of a process. A spontaneous process is one that proceeds on its own without any external influence. For example, if ice is left out at room temperature, it melts. Similarly, if we burn coal in air or oxygen, it will continue to burn naturally. Note that, in this case, a matchstick, an external factor is required to initiate the process. Once initiated, the coal continues to burn without any requirement of external factor. Thus, a process which under some given conditions may take place by itself or by initiation is a spontaneous process. Note, when we use the term spontaneity, it does not imply that the process occurs instantaneously or fast. It simply predicts whether the process has a natural potential to occur. Alternatively, if a process takes place only after energy is supplied to the system, then it is called a non-spontaneous process. For example, to prepare tea, we have to heat a cup of water. For this, we need an external factor, burner. Heating requires continuous supply of gas. Thus, this is a non-spontaneous process. Now, let's look at some spontaneous chemical reactions. When octane burns spontaneously in oxygen, it gives carbon dioxide and water. Heat is evolved. Hence, the reaction is exothermic. The reaction can be illustrated as shown here. As seen in the diagram, the reaction is accompanied by evolution of heat. That is, the enthalpy of the products is less than that of the reactants. Thus, we can conclude that a reaction is spontaneous because it is accompanied by a decrease in enthalpy. Or, we can say that decrease in enthalpy is the criterion for spontaneity. Now let's consider another spontaneous reaction. Dinitrogen pentoxide decomposes spontaneously at room temperature into nitrogen dioxide and oxygen. This reaction, although spontaneous, is endothermic. From this, we can conclude that spontaneous processes are generally exothermic. But some endothermic process may also be spontaneous. Thus, decrease in enthalpy is not the only determining factor for spontaneity. Let's look at another criterion for spontaneity. We have with us a container with a partition. We filled each side of the container with two gases, A and B, that do not react with each other. When we remove the partition between the gases, we observe that the gases mix with each other spontaneously and completely. At this point, the system is not organized, it is chaotic. In other words, randomness of the system has increased. Thus, we can conclude that the tendency of a system to acquire maximum randomness is another factor that is responsible for the spontaneity of a process. Thus, we can conclude that the tendency of a process to be spontaneous depends on two factors: tendency for decrease in enthalpy and tendency for maximum randomness. We know how to measure enthalpy change of a system. But how do we measure randomness of a system? Randomness or disorder of a system is expressed by a thermodynamic state function known as entropy and is represented by the letter S. For a given substance, the solid state will have the lowest entropy, while the gaseous state will have the highest entropy. The entropy of the liquid state will be in between the entropy values of solid and gaseous state. This is because of the way the molecules are structured in each state. The entropy change of a system depends on the rearrangement of atoms or ions or molecules from the reactants to form the products. Greater the disorder in an isolated system, higher is its entropy. The change in entropy is indicated by delta S. Its value is obtained by subtracting the entropy of the initial state from the entropy of the final state. But during the process, there is also a change in energy of the system. So, let's see how entropy and heat are related. When a system absorbs heat, the molecules within it start moving fast due to increased kinetic energy. This causes a high amount of disorder in the system. If the same amount of heat is absorbed at lower temperature, the disorder of the system will be more than what it is at higher temperature. This is because at lower temperature, randomness is very less. So, as temperature increases, randomness increases. While at high temperature, the molecules are already randomly distributed. Thus, we can conclude that entropy change is inversely proportional to temperature. This is expressed as delta S equals heat absorbed reversibly divided by temperature T. Now, let's see how it relates with spontaneity. Returning to the example of mixing the two gases in the container, this process does not involve any exchange of matter or energy with the surroundings. Hence, this is an isolated system. When the gases mix, there is an increase in randomness, resulting in an increase in entropy. Thus, we can conclude that for spontaneous processes in an isolated system, the entropy is positive. Now, let's consider the example of cooling a cup of tea. This is not an isolated system, because there is exchange of matter and energy with the surrounding. Hence, the entropy change for a non-isolated system will be the sum of entropy of the system and the entropy of the surrounding. Note that in both examples, the randomness or entropy keeps increasing until an equilibrium is reached. That is, the mixing of gases continues till a uniform mixture is formed and the tea will increase heat till it attains room temperature. From this, we can also conclude that the entropy of a system at equilibrium is maximum, and there is no further change of entropy. Thus, delta S is equal to 0 for a process in equilibrium. We can also conclude that the total change in entropy, delta S total, is the sum of entropy change of system, delta S system, plus entropy change of surrounding, delta S surrounding, and is greater than 0. We've seen that spontaneous reactions often have a negative enthalpy. That is, the reaction is accompanied by a decrease in enthalpy. We also learned that spontaneous reactions are accompanied by an increase in entropy. That is, there is increase in randomness where delta S is greater than 0. Thus, we can say that the spontaneity of a reaction involves two thermodynamic properties, enthalpy and entropy. We've learned that entropy helps us measure the degree of randomness or disorder. But, is there a way to predict if a process is going to be spontaneous? In the 1870s, J. Willard Gibbs, an American mathematical physicist, developed the concept of free energy to predict the spontaneity of a process. Today, the term free energy is called as Gibbs energy. Gibbs energy is represented as G and is calculated as free energy. G equals enthalpy of system H minus product of absolute temperature T and the entropy of the system S. Based on the equation, Gibbs energy of a system in initial state, Gi is equal to the enthalpy of the initial state, Hi minus the product of absolute temperature and entropy of the initial state, Tsi. Similarly, Gibbs energy of a system in final state, Gf, is equal to enthalpy of the final state, Hf minus the product of absolute temperature and entropy of the final state, Tsf. Thus, change in Gibbs energy, that is, Gf minus Gi, equals change in enthalpy. Hf minus Hi minus product of absolute temperature T and change in entropy S, Sf minus Si. That is, delta G equals delta H minus T delta S. This equation is known as Gibbs-Helmholtz equation or Gibbs energy equation. Let's see how Gibbs energy is related to spontaneity in irreversible reactions. We know that the total entropy change of a system which is not isolated from the surrounding is calculated as delta S total equals delta S system plus delta S surroundings. Let's consider a system in thermal equilibrium. The temperature of the surrounding will be the same as that of the system. We know that increase in enthalpy of the surrounding is equal to decrease in the enthalpy of the system. Thus, enthalpy change of the surrounding, delta H surrounding divided by temperature T, will be equal to the negative enthalpy change of the system, delta H system divided by temperature T. Thus, the entropy change of the surrounding, delta S surrounding, will be equal to enthalpy change of surrounding divided by temperature, which is equal to minus enthalpy change of system divided by temperature. On substituting the value of delta S surrounding, we get delta S total equals entropy change of system, delta S system plus minus enthalpy change of system, delta H system divided by temperature T. On multiplying both sides with T, we get T delta S total equals T delta S system minus delta H system. But we know that for spontaneous processes, change in entropy delta S is greater than 0. Thus, we can rewrite the equation as T delta S system minus delta H system is greater than 0. Now to write this in terms of Gibbs energy, we need to convert the negative enthalpy change to positive. Thus, we will take out the minus sign and the equation becomes minus into delta H system minus T delta S system is greater than 0. But delta H system minus T delta S system is equal to change in Gibbs energy delta G. Thus, we can say that minus delta G is greater than 0. This means that delta G will be less than 0. Therefore, delta H system minus T delta S system is less than 0. But delta H system minus T delta S system is equal to minus T delta S total, which means that minus T delta S total is less than 0. This means that T delta S total is greater than 0. But when the value of delta S total is greater than 0, it indicates a spontaneous process. This means that change in Gibbs energy less than 0 indicates spontaneous process. Therefore, we can conclude that if at constant temperature and pressure, change in Gibbs energy delta G is negative, that is, less than 0, then the process is spontaneous. Similarly, if delta G is positive, that is, greater than 0, then the process is non-spontaneous. And if delta G is equal to 0, the process is at equilibrium. Now, let's look at Gibbs energy for reversible reactions. We know that during a reversible reaction, a process or reaction can proceed in either direction simultaneously, so that a dynamic equilibrium is set up. Reversible means that the reactions in both the directions should proceed with a decrease in free energy, which seems impossible. This is possible only if, at equilibrium, the free energy of the system is minimum. If it is not minimum, then the system will spontaneously change to the configuration of lower free energy. Thus, the criterion for equilibrium, that is, when A plus B in equilibrium with C plus D, implies that delta Rg is equal to 0. Delta Rg is the Gibbs energy change for the reaction and is equal to the difference in the enthalpy change of reaction, delta Rh, and product of temperature T and entropy change of reaction S. At equilibrium, delta Rg equals 0, which means that at equilibrium, delta Rh equals T delta Rs. If all the reactants and products are in standard state, then delta Rg becomes delta Rg naught. that is, change in Gibbs energy at standard state. This can be expressed as delta Rg equals delta Rg naught plus RT log K, where R is gas constant, T is absolute temperature, and K is the equilibrium constant for the reaction. This can be further expressed as 0 equals delta Rg naught plus RT log K, or delta Rg naught equals minus RT log K, or delta Rg naught equals minus 2.303 RT log K. Therefore, we can conclude that if change in Gibbs energy at standard state, delta Rg naught, is negative, that is, less than 0, then the process is spontaneous. Similarly, if delta Rg naught is positive, that is, greater than 0, then the process is non-spontaneous. And if delta Rg naught is equal to 0, the process is at equilibrium.